Okay, today we're going to talk about a special type of functional group called an epoxide. What an epoxide is, it's an ether. More specifically, it's a three-membered ring. So an epoxide has this basic formula right here. And it's much, much more reactive than a normal ether is. And we'll get to the reactivity in just a moment. First off, we want to talk about how to make them. And we'll have a couple of different ways of making epoxides, but the first way of making an epoxide is by reacting it with something called a peracid. A peracid has this basic formula. It looks an awful lot like a carboxylic acid, but it has an extra oxygen in it. And the most commonly used peracid for epoxidations is what is called MCPBA. It's short for meta-chloroperbenzoic acid. And it looks like this. And essentially, you react an alkene with this peracid, and you get an epoxide. Now, the mechanism of this reaction is one that uses the most arrows, but still just one step. And there's a couple different ways you can draw it. That's what's known as a concerted reaction. In which the lone pair on this oxygen goes to one of the carbons. The pi bond goes up to that oxygen. And this pi bond going to this oxygen is going to break the oxygen-oxygen bond. That's going to flow between this oxygen and this carbon. And then that's going to kick the electrons from the carbon-oxygen bond over to this hydrogen. And these electrons from the OH bond are going to go onto the oxygen. So that is 1, 2, 3, 4, 5 arrows. It's an irreversible process. In fact, let's try this. Go ahead and copy that. And go what the arrows are showing. Okay, the pi bond goes to that hydrogen right there. What that means is you're breaking the pi bond and creating a new oxygen-hydrogen bond. The bond from the oxygen-hydrogen is going on to that oxygen. So that means is you're breaking the OH bond and you're putting a new lone pair on the oxygen. This lone pair here is going to this carbon. So you're getting rid of that lone pair. And you're creating a new bond to that carbon. this pi bond is going up to that oxygen. So what you're doing is you're creating a new bond to that from that carbon to that oxygen and getting rid of the pi bond. This bond here between the oxygens is moving between the oxygen and the carbon. And there we go. Or to put it more cleanly, we get the epoxide and a carboxylic acid. So, now, this is a concerted reaction, meaning everything is forming in one step. That means this double bond does not have a chance to rotate. Another way of putting it, cis stays cis, trans stays, cis stays cis, trans stays trans. So you started out with a cis alkene, and you do the epoxidation with, say, MCPBA, get your epoxide, and get your two methyl groups. And they end up cis to each other. Now you could have drawn it like this, but those are the same, so you draw one of them, one of those molecules. Now if you start out with the trans, do MCPBA, so if this methyl is a wedge, the other methyl has to be a dash. And you could have also done it the other way. Now these molecules are enantiomers of each other. And so, since they are enantiomers, you draw one of them. Doesn't matter which one you draw. And you write racemic. Okay. So, reactions of epoxides. Epoxides you can think of as spring-loaded electrophiles. They react in SN2 reactions. They very rarely do SN1, E1, or E2. They primarily just do SN2 reactions. Now, the thing about these, though, is there are actually 2 alpha carbons attached to the group that's leaving. And depending on what conditions you use, you can get attack at either side. Under basic conditions, you attack the less hindered side. And notice during this entire process, the molecule never went achiral. And so if it started out optically active, since it stayed chiral throughout the entire process, the product is optically active. Now, this is one of the few cases where a neutral oxygen is a good leaving group in an SN2 reaction. The other cases are OTS, OMS, and OTF. This one's a good leaving group because of the strain on that 3-membered ring. Under acidic conditions, nucleophilic attack occurs at the more substituted side. Now, methanol is not as good of a nucleophile as methoxide is. Methanol is a weak nucleophile. And you're under acidic conditions, so you can't form methoxide. But what you can do is you can protonate. You can use either protonated alcohol or the sulfuric acid to protonate the epoxide. What that does is it activates the epoxide. And then the alcohol attacks from the more substituted side. This is akin to oxymercuration. Where water attacked the more substituted side, it's the same way here. Then all I had to do is take the proton off. And have this. Okay. Now, this is still an SN2 reaction. That means the alpha carbon is inverted. Now, you might be thinking, well, that's a wedge, it stays as a wedge. No inversion took place. Well, it did. It was a wedge going to the bottom of the page, now it's a wedge going to the top of the page. You can double check this by using R and S. That's an S chiral center. That is now an R chiral center. So an inversion did take place. Remember, this molecule, if you rotate that sigma bond 180 degrees, it's the same as this molecule. And that's makes it a little bit easier to see the inversion. Okay, now go ahead and draw out the products, what you'd get if you were to take this epoxide and react it with sodium hydroxide and water. What do you get? And take the same optically active epoxide and treat it with acid and water. Now I'm using catalytic of acid because you never want to use a lot of sulfuric acid on a lot of these substitution reactions because you can start getting side reactions. Here's sodium hydroxide. You can use catalytic amount of this or not. It doesn't matter. Here you really should use a catalytic amount to avoid messes. But regardless, what's the product? Then once you get the product, what is their relationship? So go ahead and pause the video for just a moment, draw out the products, and figure out what the relationship between those two are. And here's the answer. These molecules are enantiomers. In base, you attack the less hindered side. In acid, you attack the more substituted side. Keep in mind that very careful word choice, less hindered, more substituted. They're not completely opposite of each other. They're close to being opposite of each other, but not completely. So, predict the products of these two. Go ahead and pause the video. Okay. In this first case, this alpha carbon and this alpha carbon have the same substitution. As a result, you're going to end up getting a mixture. This is if it attacks the right-hand one. This is what you get if it attacks the left-hand alpha carbon. And both are optically active. Both of them will be major products. It'd be hard to really say which one is going to be major over the other one. And that's just because they're equally substituted. Now on the bottom case though, alpha 1 is less hindered than alpha 2. So the major product is going to be the reaction that occurs on alpha 1, the substitution. Now you might have noticed that I have a very particular way of drawing this. I keep the epoxide oxygen as a line, and if the epoxide oxygen is going to the top of the page, I draw the OH that you get from the reaction of the epoxide to the top of the page. Like so. And then I have the nucleophile come in on the bottom of the page, and I have that drawn in as a line. Then I have the top of the page. I draw your other substituent. So up here you get both because they are equally substituted. Here, if one is preferred, because it is less hindered. Okay. Now, what's beneficial is to start thinking about reactions sorbent pairs. This combination here of NCPBA followed by sodium hydroxide and water Now let's draw the products out. After the first step, you get the epoxide. And then at the second step, you have hydroxide add. In this case, hydroxide is going to add to the less hindered side. So if that epoxide oxygen was a wedge, the nucleophile comes in as a dash because of backside attack. You start out with something that's achiral, he made it chiral, so you're going to get a racemic mixture. These conditions together add 2 OHs across an alkene anti to each other. Now if we added it with sodium methoxide and methanol, or if we had the second step, acid and an alcohol like methanol, what we do is add an OH and an OMe across an alkene. The difference being where the OMe ends up. In case of base, ends up on the less substituted side. Sorry, not less substituted, less hindered side. I have to be more careful. And if you're doing an acid, the OMe ends up on the more substituted side. Okay. Now, that's all I have for this lecture. I will post a problem set. Also, keep in mind that there is a take-home quiz. And it's due on Friday. So please upload your answer. It can be a picture of the page. I would prefer a PDF, but a lot of you don't have access to scanners, or your phones don't upload things as a PDF, so you can just upload a picture. PDFs make it easier for me, but I can definitely use other picture files. So just upload your answer. By Friday. And the way you access it is on Canvas. You click on grades. Then you should be able to click on Take Home Quiz 3.